This video is on lattice energy. Lattice energy is the reason why ionic compounds form. Okay, we would consider it to be the thermodynamic driver in the process. Now, what you understand is to form an ionic compound requires several steps, which I'm going to go through in a minute. But the key idea is at the end of the process, once you have, and this is the final step here, once you, you have to first form the ions, and they have to be in the gaseous state. Once they're in the gaseous state, the two ions can then, which are mutually attracted to each other by Coulombic forces of attraction, I'll put in a Coulombic, force of attraction, whenever you move things close to each other that are attracted either by gravitational potential energy or by Coulombic forces, the same thing happens in terms of the energy of the situation. Energy is always going to be released. So if you move a positively charged cation next to a negatively charged anion, the delta H for that process will always be a negative exothermic value. Now, how big a negative value that is, how much the lattice energy is, will determine several things. Because if the delta H, if you end up with a very low energy lattice, and by the way, this is your crystal lattice here, right? So this is your crystal lattice, and it's made of interlocking cations and anions. So you have your anion there, and you have a cation there, and an anion there, and basically you have this pattern in which all the anions are surrounded by cations, all the cations are surrounded by anions, and they're all essentially sticking to each other because they're attracted to each other because opposite charges attract. All right. Now, how strong how large a value this lattice energy is going to affect several variables. So if a lot of energy is released during the process of formation of this crystal lattice. Let's say we're talking about, this is a picture of NaCl, right? So this is an ionic compound. This is your cation. This is your. If there's a lot of energy released, that means that lattice is very stable. And what that's going to mean is we're talking about it's going to affect melting point. So if it's very stable, your melting point is going to be a high value. That also means your boiling point is going to be a high value. That may also affect things like solubility, right? Something solubility has to do with several variables, but one of it is the comparison of how attracted are the ions to the water versus to each other. If you have a very stable ionic crystal, it's probably going to be something that's insoluble. So if something's very stable, it may be insoluble. All right? Oh, and, I'll talk, just to remind you, these things are brittle, by the way, which is because of the very organized structure, and because if you hit them, the anions can align with anions and they'll repel each other. These guys are designed in such a way that every anion is surrounded exclusively by cations and vice versa, so particles do not repel each other in the lattice. What I want to talk about right now is this diagram over here in the upper left-hand corner of the page, and I want to talk about all the other things that happen in the process that leads to the formation of an ionic compound. And we'll notice a general trend in terms of what parts of the process are exothermic and which parts of the process are endothermic, which leads to an overall delta H that's usually a negative value. So let's start at the right here in this diagram. We're going to start right here. This is your start point. This is the ending right here, because this is the LiF solid, right? Ionic crystal lattice that has formed from the reaction of solid lithium. That's what you're starting with, and fluorine as a gas. Now, for this to happen, it has to happen in several steps, some of which have a delta H that's negative and some of which have a delta H that's positive. So let's look very carefully and let's label each of these steps, And they're using E instead of H here, but so we can use delta E instead of delta H if you want, right? So delta E, right, because we could be doing work or something like that. All right, here we go. So the first thing we do is turn solid lithium into silicon as a gas. Well, that's fusion. That's sublimation. Sublimation is always absorbing energy. So that's got a positive delta E automatically. All right. The next step, once you turn lithium into a gas, is to turn it into an ion. Now notice it's also got a positive delta E, and that should make sense because lithium starts like this, 2-1, and you're and remember, there's a nuclear charge here, right? So there's +3 in the nucleus, right? And it's holding on to these electrons, right? If you want to take that electron away, right? you need to add energy, right? It's an endothermic process. Okay, we saw that in the photoelectron spectroscopy. We're seeing that as a consistent trend. Removing an electron requires the absorption of energy. It's automatically an endothermic process. The third step, and this is something we really haven't talked about, but that's very important here, is we're going from F2 to F, which means we're essentially, what we're doing that last step is we're basically going, you get F, right? We're breaking a bond. Whenever you break a bond, I mean, the whole point, the reason why the diatomics are diatomic is because as a diatomic element, they are stable in that molecular structure. You break that bond, they become unstable, higher energy. So automatically, this is also going to be a positive delta E. So far, nothing here, okay, is an exothermic process, right? But the last two steps are, and one of them is far larger than the other. The first step involves the formation of the anion. So forming the cation is always going to be an endothermic process. Forming the anion is often, not always, okay, forming the anion is going to be an exothermic process, because when that electron ends up joining when you form the fluoride ion, essentially, you've got a negative particle moving towards the nucleus. And because of that attraction for it, okay, as it moves closer, the energy is released and you get a negative delta E. So delta E is negative. The last step, though, is the biggie, and that's the energy released during the formation of lattice. Because at this point, you have a cation and anion. And we're back to this diagram here. This is the last step here. When they come together to form the crystal lattice, and a lot of energy is released. Were it not for this final step here, the overall delta E would not be a negative value, and the formation would not lead to the formation of a stable substance. Okay, moving on. So what is expected on the AP kind of is to be able to give an idea of what the relative amount of lattice energy is based upon the formula of the compound. Now this formula that you're looking at looks a lot like the gravitational potential energy formula, and it really should. Now they're never going to make you do the math, and so this constant, which I do not even know the number of, it's in the textbook somewhere, we're never going to use because we're never going to calculate the actual value for lattice energy. That's not required. So since this is always the same number, we can just sort of ignore it, even though we know it's there if we ever really had to do a calculation. Now, Q1 and Q2 are the charges of the ions, right? And they're always whole numbers, so they could be like +1 and -1 if this was like NaCl, right? If it was like Mg and O, then instead of a +1, it'd be a +2, because, lost the top of my cue. It'd be like a +2 and a -2, because that's the charges on the ions in this crystal, in this ionic crystal. Now, and again, I don't think you're ever going to get this formula in the AP exam or ever have to use it. For some reason, the textbook calls this R, which is the shortest distance between two centers, which in my opinion, it really should be D for the diameter of one circle, or should be just D for distance between the nucleus, the nuclei of the two atoms in the crystal lattice, right? Something like that. But it's basically the distance from this point to this point, whatever that value is. Now the way this thing works is, okay, the closer that this, so you have two variables that go into here, right? So on the top you have the charges, on the bottom you have the distance between the nuclei. As a general rule, and I'm going to put a big star in this, okay, a bigger charge difference, okay, leads to a greater lattice energy, and it's a more important variable than the distances. The distance don't vary by nearly as much. So if you're comparing two things, and one of them is a +2 -2, and the other one's a +1 -1, the +2 -2 is, regardless of the size of the atoms or the ions here, is going to be the more important of the two variables. I think the best way to do this is to look at a question or two. So I'm going to go on to the next slide and show you a sample question, and we can flesh this out more in the classroom. Here we go. All right, so let's say you're looking at NaCl versus NaF. All right, now there's a slight difference in the size of the fluorine and chlorine ion. Okay, so if you look at this, though, if you put this in here, you have +1 versus -1 on the top, and this is +1 and -1 on the top, right? However, okay, now I'm not going to put a number in the denominator here, okay? NF is clearly smaller than Cl, so that makes the number down here smaller. Okay, so therefore the value for the, right, so let's make sure we're clear. The number down here is going to be larger. And I hope you all understand it, because the electron configuration for chlorine is 2-8-8 after it forms its anion. And for the fluoride, it's 2-8. So clearly the fluoride, which has one less energy level, is a smaller size. So the distance between the two nuclei will be shorter between Na and F. Now, if your denominator is smaller, that makes the overall value a larger value. Therefore, we would assume that this is more stable. Now, when comparing things that are have a different charge, okay, what happens is the charge becomes much more important. I just lost a pager. Let me go back. Whoops. Yep, there I am. Okay, so I'm on MgO, okay, and these guys have similar electron configurations, and yes, there'd be a slight difference in size due to the nuclear charge, but it wouldn't be that dramatic. What's important here is this. For MgO, you have a +2 times a -2. In effect, given that R for this one and for this one are both kind of close to each other, if not exactly the same, you can assume that this guy here is going to be like 4 times more stable. Or at least, I shouldn't even say that. I'm going to erase that. Not 4 times more stable, but we can definitely say the lattice energy will be about 4 times greater. Depends on other factors in terms of the stability. I shouldn't have said that. All right? But I can definitely say that the lattice energy will be about 4 times greater. And if I were to do something like with aluminum, now don't worry about the subscripts here because that throws students, right? If I'm dealing with aluminum, like oxide, which is +3, -2, that would even have a greater lattice energy, like maybe 1.5 times that, because it kind of multiplies out to 6. All right? The general rule is the charge difference is more important than the distance between the nuclei. So when they do comparisons, they tend to do comparisons in which one of the things has a greater charge difference or a distinctively smaller charge difference, or in which the charge difference is exactly the same, so you can focus on the ionic radii when determining the strength of the lattice energy.